sort of label or descriptor that tells you what's going on. So there's a bit of a challenge in activity recognition in terms of terminology, and there's no sort of universally accepted terminology, and I'll say some of this goes back to the 70s. Hans Helmut Nagel first started talking about events and actions in history and things like that. So loosely, we're going to use the definitions that I have here. So we talk about events, and the one thing about an event is it's a single moment in time, right? So the moment a door closes or something changes right in the imagery, typically we refer to that as an event. A little bit higher up, perhaps thinking, is this basic idea of movements, or sometimes referred to as actions. And these are, I'm going to describe as sort of atomic movement patterns. So, sitting down, or waving, or something like that, could be thought of gesture-like. You could describe it as a trajectory in some feature space, whether it's the feature space of the joints of the body or some appearance. It is that it's a single thing. And then at the higher level, there's this notion called activity. By the way, one of the reasons it says adopted from Vanu and myself, not together. I did the original paper on movement, activity, and action, and it was wrong. I mean, wrong in the sense of, in hindsight, I had activity followed by actions because I was thinking of actions being a big scale thing. And the field, which liked the paper for a little while, has sort of moved on, and we have this notion of movements and then actions and then really activity. And activity is being sort of composed of a series of actions or a bunch of actions happening at the same time. Typically, if you're looking at some interactions amongst a group of people, that would be thought of as an activity. So one example, here's a thing taken from some surveillance work. Some of this was shown at the PETS conference. Let's see. Performance Evaluation of Tracking and Surveillance, I think is what PET stands for. There's been a lot of work lately on just, finding the person in the image here and have extracted them there, and maybe looking at some interactions between people in a train station. The idea of basically being able to watch an environment, sometimes to be able to inform authorities if there's possible problem going on, sometimes to do things forensically, right? So something happened, and I'd like to look back over the last 8 hours of video and find different kinds of things. So there are a couple of basic activities of doing activity recognition. One I'm thinking of as model-based action recognition. So you have some way of getting the pose or the appearance of a human body, and you're going to relate these descriptions of the change of the pose or appearance to some action labels, and probably build a classifier or something like that. And one of the main challenges in doing that work is, are your data that you use from training taken from a different context than the data where you're doing the actual recognition? These problems tend to be pretty easy if I have training data from the place that I actually, and the camera in which I want to do the recognition, and are much more difficult if the training data come from a different source. Model-based activity recognition basically assumes I've got some low-level process for either detecting actions, maybe probabilistically with some noise, and then what I need to do is recognize the overall activity by comparing it to some, I put structural representation of the activity, something that defines how the different actions relate one to the other. One of the reasons I sort of like talking about it this way is it's sometimes reasonable to get lots of examples of low-level actions, so you can do our traditional building a classifier to do that, but harder to get lots of examples of the overall activity. There's some change in that lately in terms of using large data sets. I'll talk about that a little bit, but in some sense, those are a somewhat artificial problem. When you do this, you have this problem of handling uncertainty. That is, your low-level detections are uncertain, and your descriptions vary, and you have to be able to recognize the activity in the presence of this uncertainty. And some of the major challenges are, just can you keep track of which part is which, who is who? If you've got multiple things going on in a train station, there's lots of ambiguity and occlusion, and being able to say what the activity is sometimes difficult when you're subject to those variations. Recently, there's been some work where you actually don't do as much about that. You just view activity as sort of a big space-time pattern of some sort. So you're not actually tracking bodies, or you don't even know there are people there. You're basically just describing the overall pattern of motion, and you typically train a classifier. We'll mention that just a little bit here, but not spend a lot of time on that. Also recently, and this was kind of, I found it kind of funny, there's been doing activity recognition from a single image. And you might ask, how is that possible?
How is that possible?
Okay, thank you, Megan. I didn't really want her to say anything. Yes, how is that possible? Well, look, here's a picture, okay? So you see that it says, imagine a picture of a person holding a flute. Well, you don't have to imagine. There it is. You could say, what are they doing, right? And you could say, they're playing a flute, right? Playing a flute is an activity. So even though I'm only recognizing a particular pose, in fact, when I go like this, you can almost hallucinate the flute being there, right? Even though it's not really there, and you can think about whether that's a vision problem or an AI problem or a hallucinogenic problem, but whatever it is, the idea is that you're recognizing activity from a single pose, and I don't really think of that as activity recognition. What I think of that is representative image recognition, right? This is sort of the canonical image that you have in your mind of the pose of a person doing that activity, so you're recognizing the pose in the context. You might even be recognizing the flute as is here. I guess you could play fruits too. I don't know. You could recognize the flute, and that helps you see that they're doing flute playing. But to me, it's kind of a far cry to call that actually activity recognition in terms of anything like video. So let me tell you what we're not going to cover. In exactly the same way we talked about bag of words for recognition of objects, where you have some way of finding interest points in an image, and then you cluster all those interest points into code words. Remember that? And then you describe each image by its histogram of the code words, and then you build a classifier to recognize these histograms. Well, you can do the same thing in video, right? So you can pull out these little interest points. This guy's moving and his hand is swinging, or over here, or maybe this car is moving. And that would build you could extract some features. But now, remember the volume of video? Your feature points, your interest points are in space-time instead of just in space. And you could pull out little space-time patches, sometimes called cuboids in some of the work, where they're just these little chunks of space-time imagery, and that builds you your descriptions. You can then do feature quantization to learn code words. You do this over all your videos. Then for an incoming activity, you can look for the interest points, you can build a histogram of these code words, and then you can train a classifier. And here they talk about using an SVM with a chi-squared kernel. The reason we're not going to talk about that, although that's good work and interesting work, is it's in some sense only the three-dimensional, from 2D XY to 3D XYT. It's just the three-dimensional extension of the previous work done on bag of words or things like bag of words. Instead, we're going to talk a little bit today and then also next time on some representations that fundamentally are about how things move or about time series. So I'm pretty sure we showed this before when we were talking about motion and perceptual organization. And as it says here, even impoverished motion data can evoke a percept. And presumably, you all see these moving dots as a person walking, right? So you're not recognizing this as a person from the appearance of the dots. You're recognizing this as motion, and then you see that it's a person. And in fact, I can prove that to you looking at some work that was done by myself and Jim Davis, now professor in Ohio. And so I'm going to show you here. So when you take a look at this picture, unless you've seen this demo before, you probably don't know what that is. When I put this thing in motion, what do you see? What you all probably saw was somebody sitting down. And what's interesting is now when the video's done, you can sort of see that, oh, this is a person standing up right here, right? In fact, there's some sort of a blackboard behind them. And then once they sit down, their head is here and the body's here because there's actually a chair over here. But until that motion happens, you can't actually recognize that. So we did a little bit of work on some technology that would let you recognize this, and we created this thing called motion energy images. So here you see a picture of a person. This is a clear video, all right, where the person's sitting down. That's, by the way, Claudio Penhanes, who also got a PhD in computer vision, now doing great stuff down in Brazil. And what these are representing are cumulative images of where stuff has moved. Okay? So the idea is, when you're all done, this is the area in which stuff has moved. And, you know, the question is, that's somehow indicative, that something about that pattern and how it moved in there is indicative of the actual motion pattern itself. So can we recognize that explicitly? So we created this thing called motion history images, which becomes the motion energy images also, which are a function of the temporal volume. And what I mean by temporal volume is that same thing, right? X, Y, and T. So I've got a collection of video. And it's really a very simple recursive computation. This is an MHI image, motion history image. And the way it works is quite simple. As each new frame comes in this particular case, you run some algorithm to tell me which pixels are moving in that frame. Now, of course, this is under the assumption of a static camera, and if you're not using a static camera, you'd have to compensate for the motion of the camera, threshold out the motion of the person, all the usual caveats. But then, when you do that, you get this very simple operation. If a pixel is moving, set that location at time t to some maximum value tau. And you're going to pick tau. Maybe tau is 15. I'll tell you why 15 in a minute, right? And if it's not moving, that's the otherwise, I'm just going to decrement, decrement the value, okay, from the previous time, but I don't go any less than 0. So the image on the right is an example. The brighter pixels, like over here, they've moved more recently. So if this is time t, maybe they've moved at time t minus 1. They just moved before. So they started out as tau. So maybe tau is 15. Actually, let's make it 30. That example will work better. It was 30, so now it would be 29. But the pixels up here, they moved, the last time they moved was 15 frames ago. So its value would be now tau minus 15. So if tau were 15, it'd be 0, so that'd be black. That's why it didn't work so well. But if tau were 30, t minus 15, it would be now down to 15, right? It would have counted down to 15. So these areas are nice and bright white because they just moved. These areas are darker gray because it was a longer time ago that they moved. And so the way you can think about this motion history image is that it both shows you sort of where stuff has moved, and it also shows you sort of how stuff has moved, because you can tell that the stuff up here moved a long time ago and stuff down here is moving more recently. It's a recursive filter. That is, I only have to keep track of I of tau of x, y, and t minus of t, and I can create the new one when the next frame comes in. So I don't have to remember my old frames. The other thing is, where did tau come from? Well, the pixels go from tau down to 0. So let's suppose I'm bringing in 30 frames a second. So if I set tau to 30, then from 30 to 0 is a range over a second. And what that would mean is that anything that happened longer than a second ago, I'm not worrying about. So I'm recognizing action that's the length of a second. Suppose you wanted to check whether something could happen slowly, right? Like he sits down slowly. It takes him a full second to sit down because he's really slow. Or somebody sits down quickly, right? Because they go like this, and they go, that's not Megan playing with the video. Anyway, so they can do it in a tenth of a second. So, in a third of a second. So that'd be tau of 10, right? 10 frames. Well, one of the kind of cool things about motion history images is if you give me the motion history image of tau, right? So everything goes from, let's say, 30 to 0. I can just, if I wanted the motion history image for tau equal to 20, I could just subtract 10 from it, right? So 30 becomes 20, and anything that's less than 10 just becomes 0. So it only looks back 20 frames. So it's trivial to compute I of tau 20 from motion history tau 20 from motion history tau 30. So I only have to keep one around, whichever one's the longest one, and I can check all of those time windows at the same time. And then also, as should be clear, if this is the motion history image that goes from white to dark, if I just wanted the motion energy image where anything has changed, all I can do is just threshold that picture, right? Anything greater than 0, make a 1, otherwise it's a 0. We can take these two images together, these motion energy images and this motion history image, and together we referred to them as what we called a temporal template. It was just a model of how stuff moved. All right, and then we tried it on a data set that we created. We had this person who was way more fit than we were do a whole bunch of different aerobics, different moves, and we just said, okay, can we now recognize if now she's doing a new routine, which aerobics move she's doing? All right, and One of the interesting things that you can see here, what I'm showing you here are the MEIs. All right, I'm just showing you the binary version. And you might say that this